good. Sorry if you got to look at my menu bar. Okay, cool. I'm Brent. I'm from CoreLogix. I'm a software engineer there. You can find me on such places as GitHub. I'm here to talk to you today about our OOM Guard and what it is and what it's done for us, which is prevent out-of-memory errors. So first, I gotta tell you a little bit about ourselves, just to set like a background so you know why we even care about this thing. So we're a log analytics company. We run some decently sized clusters that are Ballista-based, which for those of you who are unfamiliar, is one of the ways that you can distribute DataFusion. Also, we're a multi-tenant environment, so we have lots of users on shared clusters, always submitting queries, and we run the full gamut. We have like interactive stuff where people are trying to query their log files and they just want instant results, and adapt those queries and run them again. So, that's in the second range through, a couple minute range, all the way up to like our background queries, which I think have a 20-minute timeout, something like that. I don't know. And it's all structured logging data. So it's all JSON that's been encoded into Parquet and stuff for queryable with DataFusion and Ballista. So normal flow for queries within CoreLogix. User runs a query gets an error. Okay, this is the normal error flow. Normally they don't get an error. Server logs the error. We ship that log through our own log shipping service back to ourselves, and we can analyze that later, and server keeps going and everything's fine, like just normal life, right? In the OOM case, it's not so good. Like here, the user runs a query runs out of RAM, Kubernetes, C group thing, OOM killer says nope, and you just get like some sort of sig kill, I forget what it is, 139, and you don't have a chance to do anything. So this is very hard to diagnose. We have a very smart guy on our team who has created a query that finds queries that start but don't end. It's really expensive. It's like a self-join. And anyway, you don't want to do that. It would be nice. Well, plus when this happens, like I think my Nathaniel can attest to this. I got called when we didn't upgrade, and all of a sudden 80 of our executors went down, and then they retried, and then 80 more executors went down. And so pretty much there were no executors left in our cluster within a matter of seconds. So needless to say, this is not a very good situation, especially since if there's no logs, it's hard to find the query that did it. And yeah, I think we repeat a couple of times. So we retry the thing that just killed our whole cluster, which normally makes sense to our credit. So what's the obvious fix, and why wasn't that sufficient? So DataFusion, like all good databases, database engines, has a way to track memory internally. And so whenever operators allocate record batches or do stuff, they have a thing called a memory pool, and they try to register their allocation and then do it. And then when they're done with it, they free it. And so we know roughly how much memory is being used. And that should do it. And generally it does. This is probably the 0.001% case where we hit an OOM and it kills our clusters. But low frequency, high severity on that one. So I kind of compare this to like cooperative multitasking. Like now I'm really dating myself, Andrew. I grew up in like the Windows 3.1 days when like all the programs had to have a yield point and like not too so much on the main thread. And if some program hung, then everybody was out of luck. And that's kind of what this voluntary memory pool is. Like if you do all the proper accounting and you do it exactly right and everybody else does it and the world's perfect, it works. And so I'm not going to go through all the instances of edge cases here where that might not work. In fact, I haven't even checked them. I told Claude, just go look at this PR and make me a slide deck, and that's what you're seeing now. It's pretty effective. So yeah, you can check out the links if you want. So if we can't trust the pool, what else is there? Belt and braces kind of approach, right? or suspenders for Americans. So the way allocation works in Rust is every Rust thing, give or take like a few libc things, I think, go through a global allocator. And so that means anytime you shrink or grow back or change a string or do practically anything, including often panic, and allocations are happening. So what if we treat this as a cooperative yield point, going back to my like Windows 3.1 example? People might not register all their memory, or maybe if they try and register memory, we have a point at which we can stop them from going over, but maybe that's once every several seconds or once every 1,000 record batches or something. So with the global allocator, we have something that's running 10 nanoseconds to a microsecond, pretty common. And luckily, Rust lets us go hook into that global allocator. And so now we have code executing in our paths that can intercept arbitrary user operations quite frequently. So what we did was make a fairly simple thing that's just a wrapper, but allocators are a whole mess on their own. If you want to go study that, it's interesting. So we just wrap it. We use TIKV internally, and so that's just our inner A here. And we just treat this like a bank analogy. So essentially there's a budget, and if you exceed your budget, you're overdrawn. And if you overdraw your budget, we return a null pointer from the allocator, which means this allocation failed, which does not go well in Rust, or basically any modern program written to run on a machine with virtual memory. So backing up, you might ask, like, well, how can you do this if it's happening in the nanosecond frequency, gigahertz? Like, not good. So the way the allocators work internally is they have arenas, and the arenas live on threads, so you don't have to do cross-core communication. And so as long as you keep it local on the thread, these are like very fast operations. So what we do is we give each thread, or thread in this case, Tokyo worker, its own budget, and we start that out at 0. And so we say allocations, debit that, and they take it below 0, and freeze credit that. And okay, that's great, but now you have a bunch of threads that all disagree about how much memory is actually being used. So what we do is pick a constant, which I think we went with 64 kilobytes. And so if the thread gets below 64 kilobytes, it has to do a reconcile with the bank. And so there's like a central clearinghouse, and that's like this global atomic balance. And so, you have to go do whatever it takes to sync to global atomic, but fetch add or whatever, but it's amortized. Like, this is only going to come up when the threads get too far out of sync. So this all ends up like amortization is kind of the key word here. I guess the final fallback is like these allocators can drift. You can have allocator slab allocations. Like TIKV loves to just pull in like 64 gig of memory when it starts up, and it's all just virtual memory. And so you need to figure out like, well, what's actually being written to, which pages are dirty, and only those are claimed, and so on and so forth. And so only the allocator knows this, and it has to do its own cross-thread synchronization to go tell you this. And so that's kind of expensive, but not so often. We can't do it 50 milliseconds. It's tens of orders of magnitude more than we're talking about for these other operations, so it's fine. So we just have a sync thread that just goes and queries to KV and resets the bank balance to like what the true balance is every once in a while. So it all amortizes to pretty good time. There's probably some pauses in there, but nothing like Java. So yay. So one of the tricks we ran into a lot of gotchas while trying to research this and make it work, but you can't panic inside an allocator, and it's undefined behavior. And undefined behavior, I mean, heap corruption, stack corruption, like nasty things that I found out later. But you can return null. And there is this other thing that Rust has, which is a global alloc error hook. It's a nightly, but we can turn it on even without using the nightly toolchain. So when you set one of these, most code just like panics and bails, and I think the default one just does aborts process. But you can intercept this and you can replace it with your own, and that is safe code, so you can do a panic there and you're not going to corrupt anything. So we have a global panic handler, and the way that flows is worker tries to allocate, say why that's Tokyo in a minute here. OOMGuard catches that, returns null. Null gets caught with a global error hook. We get to launch panic because we're in a safe space now. That lines up the thread, which in our case is always a Tokyo worker. Hopefully the dataframe.collect, whatever operation within DataFusion is driving this. And we get a catch and wind, and we have a closure. And so in that closure, we get to store the query ID that was running. And so we know exactly which query did it and what the balance is. So we can go investigate that later, and we can log it. But at the end of the day, you get the same resources exhausted error as if you hit the memory pool limit in DataFusion. So it handles this well. Yeah, so why not just kill everything? Sometimes you need to turn this thing off. All this is saying is like, it's not an expensive operation to go check if it's off. Why do you want it off? Well, at first I just had it kill any thread that overallocated, and hyperthreads were dying, and then, background things and, important stuff died. So decided that this should only fire on stamped threads, and so we can use a thread local. And so all of our DataFusion tasks that we run, we allocate a Tokyo thread pool just for that query. And so we mark them when we do, and we know we track every allocation on every thread because that matters. But only ones that get bankrupt are actually query threads. Claude thought I could do a demo, which I was optimistic about, but I'm on a Mac and there's no C groups. And so we're going to skip the demo. But this was a savage query I came up with to like generate a really big string field and do a huge aggregation on it. And we could kill it every time. Get the OOM panic, and you see a bad error. You can turn this on, and you see a good error. OOM Guard panic, negative 84 megabytes. But the PR that this is linked to in this presentation has this turned on for the flight SQL example in DataFusion. There's an examples folder with a server that lets you run SQL through DataFusion. It's pretty cool. So yeah, like finally we can do like a select one and you get a one back. So server's still running and everyone's happy. Questions? I realize I've been talking for a long time. Yeah.
The queries come from DataFusion. Did you find that in the data set or the query that was like causing these errors and can you fix it, or did you not get
There's a separate epic within DataFusion to solve a number of bugs where accounting is not handled properly. So that's why I say belt and suspenders is this is the belt or the suspenders, I don't know which. But yeah, we're working on fixing all that stuff as well. Yeah, nightly feature, I won't get into that, but there's some flag you can set where you can pull in. Okay, I will for a minute. I thought nightly was like some branch of Rust, and the Rust compiler lived off on its own and they kept rebasing it or whatever. That's not true. It's just a set of feature flags. And so you don't have to use the nightly toolchain to pull in nightly feature flags. You can just turn them on. So we set that, and this thing has been an unchanged issue, like unchanged implementation for 7 years now. So it's pretty stable. So what's the status? Ballista, I think, has an issue. Comet is in the issue stage. DataFusion Distributed, I think, is working on their own. They were asking questions about this in the conversation. We've implemented it CoreLogix. I think it's just a general thing. Like sorry, I should have prefaced this talk by saying there's nothing specific about DataFusion to this, which is in fact why it's not in the core library now, is because it's a library. So this is something that you can enable on any server that you want to not OOM anymore. So, all right, long way to get here, but what's the result? We turned this on 1 to 2 months ago, and we used to get fairly frequent alerts and pages. And, well, used to be in the middle of the night, but now during the day. And we've had none that I know of. This thing, it seems to be, correct me if I'm wrong here, guys. It seems to be working. And so to show you our dog fooding right here, I was going to click through to a query. Okay, well, let's not do that. Here's me. Here's me running the query right before the session started, because I know it would work then. And so we can see actual instances of this firing in the last hour or so. And so probably can't really see that too much, but there's 2 of them there, 2 of them there. Usually one query, I mean, I've seen up to 400 on one query. We used to run with such crazy parallelism. But down, yeah, I'll just show you the screenshot. You believe me? So we get a nice stack trace. We get a query ID. We get the file name, the panic, and the balance when it crashed. So this has been pretty good for us. We really haven't seen memory issues ever since then. Yeah, any other questions? Yes.
You can DQ that query retry to right?
Yes, so that's a stage that we haven't got to yet. Like, I'm really interested in doing stuff as far as future research, like creating memory pools within DataFusion as a library where apps could hook into them. And you can say like, oh, I happen to have TAKV and I have an OOM Guard. I want to go inform the DataFusion memory pool with real stats from actual memory. I think we can, the query that gets killed, as far as I've seen, in practice, almost always happens to be the perpetrator, but it could not be the query that consumes 99 gigabytes. It could be the one that consumes a kilobyte at the end. So I think we can do stuff like use DataFusion memory pools. So when the OomGuard kills the victim, we can go sort descending by number of outstanding queries of how much memory they're using and also kill the perpetrator. So yeah, there's a lot of interest. I mean, Comet, I think, had some interesting stuff to do with, they're already trying to manage memory between the JVM and Rust. So there's a lot of things you can do once you have this in place. Cool.
So we have post-run crashes or something. Here's all the locked queries at the time. You have all parties involved, but you're just assuming that the next most memory consuming effect is the worst one, right? Even if query you killed has a 1 kilobyte, if you said yes, it's consuming 200. All parties involved are in the lock state kind of thing. I don't think too much Postgres.
Yeah, too much Postgres. You know, this is read only in practice. Like, we're just querying Parquet files that have been sitting out there. So there's no locks to contend over, anything like that. Awesome. Thanks, guys.
Right, let's put some file upgrades actually.